Hello, people. So I'm back with few new topics. So let's get started with all of them. Okay. So without any wasting time, let's get started. So the topic we are going to see is multiplication. Okay. It is multiplication and what it is. Let's see. Okay. So this rule is basically used for finding the joint probability, okay, or finding the intersection probability of an intersection. Okay, so it's a probability. What we know that a given b, probability of a given b, we say it by probability of a intersection b by the probability of b. Okay, we have two events. Okay, we have two events, event A, event B. What is the probability of event A given that event B has already occurred? It is nothing but the probability of intersection A and B divided by the probability of event B. Okay. But if we do some manipulation in it, okay, we do some manipulation and we can say that this we can write it into, can we? Yes, we can, because we can do it very simply. Okay. Now we can see that the probability of A intersection B is the probability of A given B into probability of B. Okay. And this is what multiplication rule is. This is what multiplication rule is, which is actually used to find the probability of intersection of two events. Okay. There would be some cases where we will be given the probability will be where we'll be given the probability, conditional probability, and the probability of an event. Okay, and we will have to find the probability of event A and event B. Okay, intersection of the probability of intersection of event A and event B. So let's see it by an example. Okay, by an example, and in this example, so suppose that I have a group of people, and in the group of people we have 60% of women. Okay, in the group, okay, we have in a group or a class or whatever group, suppose that it is a group of 100 people, and in this 100 people we have 60% women. Okay, 60% women. If we visualize this, then it will be like this is the group or the class. We can say that this is the 60%. 60% is women. Okay, 60% are women, and in the 60%, in this 60%, we have 40% women. The women are married. Sorry, I'm married. Okay. So in a group, we have 60% women, and in the 60%, we have 40% of them are married. Okay. Now we have a question that what is the probability that at any given point, if we pick a woman who is married and woman, okay, and how can we find this? So, and here our multiplication rule helps. Okay, see, so suppose that we have an event w, w for woman. Okay, w is an event where the where what I would say that the event will be woman, and M for married. You have an event M which says that the woman will be married. Okay, women will be married. And what is the probability that the of getting a woman? What? 0.60. How? Because we have been given that the percentage of a woman in the class is 60%. How much it is? It is nothing but 60%. So we have, if we change into the fraction, okay, how much do we have? Okay, 60 by 100, 0.60. Okay, probability. What is the probability of a woman who is married? 0. It has been given. Okay, it has been given that the probabilities, if we pick any woman randomly, what is the probability that the woman will be married and the woman will be married. So we have to find nothing but the intersection of woman is married. Okay. Okay. Intersection of woman is married and she is a woman. Yeah. It obviously if she is a woman and married, then it will be intersection of woman married. Okay. So, and what we know this earlier from the above, what we know, we have been got this, we have got this our equation. So we can easily put that the probability of woman is married, given that she is a woman, okay, is okay. Wait, if I say that this won't be the probability of woman who is married, this will be probability of a woman married given that she is a woman is 0.4. We don't have the probability of married. Sorry, it's my mistake. Because if I'm saying the probability of married, okay, married, then it will be from the whole class. Understand? This will be from the whole class that the person we are picking is married. Either she can be a woman or he can be a man. Okay, either. But we are saying that in the 40% of the 60% are married. So we have to only pick this 60%. So what this says that, so 40% says that this is the probability of a woman being married. Okay. So the probability of someone being married given that she is a woman. It is nothing but 0.4. I have you got this? Yeah. So this is what I'm trying to say. And two, the probability of the woman. Okay, the getting woman. What it is. So what is the probability of this will be this. So we have all our numbers 0.40 value 0.40. We'll put this here into the probability of what is the probability of woman 0.6. Sorry, 0.60. And if we do our multiplication, then 0.4 into 6, 24, 0, which will be nothing but 0.24. So at any given point, if we pick a person from that group who is married and woman is 24%. Is 24%. Have you got this? Yeah. Now, I'm going to tell you a very important thing that you must know. When to use joint probability, when to use joint probability or intersection probability. Okay, or so we use joint probability and we need a joint probability when we select someone from the entire group who has two characteristics. Okay, who has two characteristics that need to be satisfied, and we need conditional probability. Okay, we need conditional probability when we pull out we when we have one characteristic satisfied, okay, already, and we want the probability of the another characteristic or the second characteristic need to I would say what I would say not characteristic, but we have two conditions. Okay, for the joint probability, both condition should be okay, should be fulfilled. Okay, should be fulfilled. And in the conditional probability, one has already, one has already done, or I would say one has already completed. We have one completed, I would say. Okay, so according to the previous example, okay, what I was trying to say is that we had to find the probability of woman which is married. Okay, which is married. So we had two conditions. First is being married, and the second one is being woman. Being woman, and this is where we need joint probability. What we use here, but in the conditional probability, we use it when we have one condition already satisfied. Okay, satisfied. How? Suppose that what we have told that the probability of woman being married is 0.4%. So one condition is already satisfied. The person that we're picking is already married, and who is woman? Already married. Okay, so we have to find the probability of being married given that she is a woman. Are you getting it? Woman, the condition for the woman is already satisfied, but we have to find the probability of being married of that person, of that for the woman. There we need condition probability. Okay, so that was it for the conditional multiplication rules. Now we are moving ahead with the addition rule. Okay, addition rule that we use for the unions. We use the conditional, the multiplication rule for the intersection or the joint uh, for the intersection. Now we are using the additional rule, the addition rule, not additional rule, but the addition rule for union. Okay, for the union. So what this says, okay. So in the union, what we know in the union, what we say actually, if in a union, suppose that let's take example of a die. Okay, the very simple example. We have an event which says that it should be odd. The die is odd. Then what the sample is be 1, 2, 3. And we have another event which says that it is even. So wait. How 1, 2, 3, man? 1, 3, 5. It's my mistake. Sorry. It will be even. So what if even 1, 2, 4, and 6? 2, 4, and 6. Okay. What is the union of A, B? If there is nothing any common, we could we can also take the union of it. Okay, we don't have to worry about that. Is there any common between them? No. If there is not anything common, then we can still take the union of it. And what it will be the union of it? 1, 3, 5, 2, 4, 6. And if we arrange it, then it will be 1, 2, 3, 4, 5, 6. Now, if you see very precisely, then this also comes in it, and this also comes in it. So if we are finding the probability, if we are finding the probability of this A union B, then we're also finding the probability of being even and being odd, being even and being odd. Okay, or both. Okay, that it is even also or odd also. Okay, we are talking about the events, not the dice being the number. Okay, we are talking about the events, that it is odd or even. We did the union of it, and now we are finding its uh, what do we will say, the probability of the union of A and B. Okay, now if I talk about the previous example, with the help of previous example, then what is the probability of woman and union married? Okay, now we have a special case. We are not saying that in the class we had the 60% of women and the 40% men. Okay, and in the 60% we had 40% married. This was our conditional probability. But in this, we're taking the union, that what is union of being woman and being married. We're not talking about that the woman being married, only being married. So being married can be from this group also, from the 60% also, or from the 40% also. We are not giving a specific condition that it should satisfy that condition. Okay, satisfy that condition to being married. No, being married from the both group, from this or from this. Okay, or we are saying that, okay, it could be anything. That what is the probability of being a woman and being married, or both woman and married. Okay, being woman, being married, and being woman and married. Okay, so let's find it. What this rule says. This rule says this married, probability of being woman plus probability of being married minus probability of woman intersection married. Why? Why? Because we have taken uh, the the counting twice. The counting twice. Okay. Why? See, we are taking actual union of it. Okay, union of it. So union of it. So there could be more duplicates of that. Okay, duplicates of that and this thing. Okay. So suppose we have the set of women, okay, and being married. Okay, in the woman we have only person who is a woman, but in being married we have both. We have both women, women who are married, women who are married, and man who are also married. Man were also married. So we need to also minus this because this condition is being also in this. Okay. See, and also this. Okay. This is also woman, and there here is also woman and being married. So we need to uh, remove this, remove this to actually get that what is reasonable or sensible to us that we actually want to find. So that what we do in the additional in the our addition rule, that we find this woman, oh, sorry, intersection, union, married. So what is the probability of being married? We have already seen 0.60. Okay, married 0.5. Okay, now what is 0.5? It tells that 0.50 tells us the whole group. From the whole group, 0.5% people, or I would say 50% of people are married. Are married. And in the woman, okay, in the woman we have also women who are married, and here we have also women who are married. Are you getting it? Here are also women that are married, and here are also women who are married. Okay, so we need to minus this, and which was 0.24. Have you got this? Why? We have got this probability that in the 60% of women we have 40% women who are married. So we need to minus this because we have already women here who are married, and we have already some women here who are married. So we need to cut them off, cut them out, or we have to only choose one, either of them. Okay, or we need to cut one. So that's what we did here already. Now let's do our math. 110, okay, minus 0.24, which will be nothing but 0.86. Yeah. So if at any given point, if we pick a person from the group, then the 86% will be married or married. There can be married, or they could be a female, or both married or female. Okay. And this is what our addition rule says. Now moving to ahead, moving to another, we have independence. We have independence. Okay. So what does independence says? See, independence says that if an event is happening, then does it change or doesn't affect the another event, or does it affect the probability of another event uh, changes the probability of occurring of another event. Okay, so let's understand it by an example. Okay, we have uh, a dice. Okay, and what is the outcome of this? 1, 2, 3, 4, 5, 6. Okay, now suppose we have an event which says that it will be an odd, and we have event which says that it will be 1. It will be 1. The die will be 1. Okay, what is the set of it that we? What is the favorable outcome that we will have? 1, 3, 5. Okay, and for this we have only 1. We have only 1. Now we need to ask some few questions. Okay, here for this, the first question here is, so we have to ask that when die is odd, what is the probability of getting 1? When die is odd, what is the probability of getting 1? So when the die is odd, 1, 3, 5, we have 3 favorable outcome. What is the probability of getting 1? 1 by 3. See, 1 by 3. How? Because we have 1 here already. So if we are finding 1, then we have 1 here already also. Then if we want to find the probability of getting 1, then what our sample space here? 3. We have 3. Okay. And what is the probability of getting 1? 1 by 3. Simple. Now we need to ask the another question, that what when the when the die is 1. Okay. What is the probability of when the die is 1? without knowing that it is odd or not. Okay, without knowing it is odd or not. Okay, so what I'm trying to say here is actually is that does these both events affect each other's probability of getting their probability. So see, the first question was okay, and the second question we are saying that when the die is one, and we don't know that it will be odd or not, we don't know. Okay, so what is the probability of it? 1 by 6. 1 by 6, how? Because we have one which is favorable and we have the total 6, so we have the probability how much? 1 by 6. Okay, 1 by 6 when we don't know it is odd or not. But when we know that is it odd or not, it is odd or not, we have the probability 1 by 3. So you can see that the probability of being 1, whether it is odd or not, it is 1 by 3, and the probability of getting 1, whether it is we don't know that it is odd or not, it is 1 by 6. Here we know that it is odd, then its probability is 1 by 3, and we know that here we don't know that it is odd or not, so its probability is 1 by 6. So the both probability is different. The probability of both events is different. So this is not an independent event. This is an independent event. And dependent event means that uh, happening of one event changes the probability of another event. Changes the probability of another event. Okay, it affects. So suppose we have another event C. We have another event C in which it says that the die will be 1 or 2. The die will be 1 or 2. So R, A, and C are independent. Independent. Yes. So we can find the independence by using one uh, probability, which is conditional probability. Okay. So if we know that if there is conditional probability, then it changes the probability of another event. Okay, changes the probability of another event. If one event has already occurred, then the probability of another event get changed. Okay, if A has already occurred, okay, then what is the probability will of C will be not same. We know that. But what if the probability of C doesn't change even if A has occurred? Even if A has occurred. Okay. So what does our C says? The event C says. Okay, event says C says that the die will be 1 or 2. Then what is the probability of being 1 or 2? What is the probability of being 1 or 2? 2 by 6, nothing but 1 by 3, nothing but 0.33. Okay, now being 1 or 2, okay, given that A has already occurred, okay, doesn't change it means that A and C are independent. A and C are independent. Okay, so the probability of being C equals to the probability of C given that A has already occurred, and probability of being A equal to probability of being A given that C has already occurred. If both are same, then they are not dependent. They are independent. Okay, they are independent. How? Let me show you. So, what is the probability of A given that A has what is the probability of C given that A has already occurred? Nothing but a probability of C intersection A by the probability of A. Okay, and let's find the probability of A and C. So we have already found the probability of C is nothing but 1 by 3. And probability of A, what is the probability of A? What A says? A says that it is odd. A says it is odd. 3 by 6. So 1 by 2. Okay, it will be 1 by 2. How? We had only 3 outcomes that are odd. That's why it is 3 by 6 equal to 1 by 2. Okay. Now what is the probability of being uh, intersection of A? C intersection of A. It says that C intersection A, what it will be? C in the event C, what we have? We have only only two outcomes, which are two. Okay, in the C we have two or one, but in the A we have odd 1, 3, 5. Okay, what is the intersection of it? 1, 1, 1. Both are common, so 1. So what is the probability of A intersection C? 1 by 6. How? Because we have only one outcome that is favorable, divided by 6, and given probability of A, which is 1 by 2, which is 1 by 2. So 1 by 6 into 2 by 1, which will be nothing but 1 by 3. 1 by 3. Okay. And this is what we say that is independence. Is independence. How? If we see the another event, okay, given that given that C has already occurred. Okay, what did you do? A intersection C by the probability of C. Okay, by the probability of C. So let's see its probability. Okay, A intersection C. What it is? It is same. A. It will be 1. So it will be 1 by 6. Okay. What is the probability of C being C? 1 by 3. Okay. 1 by 3. 1 by 6 into 3 by 1. What it is? 0.3. Did the probability change? Tell me, did the probability change? No. Then how can we say it is independent? Sorry, dependent. My mistake. How can we say it is dependent? If the probability changes, okay, if the probability changes, then we call it dependent. Because if the probabilities or the event are dependent, then the probability of being an event, then the event of A changes the probability of C. Okay, are you getting it? If A has already occurred, then C won't uh, C won't be having the same probability at as it was earlier. Okay, got it? Now, so we could say this by saying that if the probability of A given that B equals to the probability of A, it doesn't change. It's already same. It is same. And probability of B given that A has already occurred, it is same. Because if A has already occurred and if you see the probability of B and it gets changed, then it is dependent. But if it is same, this is independent. This is independent. This is won't affected by this. And if it is same, okay, suppose that what is the let's see what is the probability of being B. Okay, okay, this is not actually from this is not related to from the previous example. I'm just telling you, you know, the variables that we use. So if the probability of being A is same after doing the conditional probability of A given that B has already occurred is will be same, then these are independent. Independent. And this is what we use in the naive bias. Naive bias. Okay. So, okay. Now, we can do another way of checking that is it independent or not. Okay, how? Suppose that what we know. Okay, we know a formula that the probability of A intersection B is something. Try to remember it. What it is? What it is? It is probability of A given B into the probability of B. Is it it? Isn't it? Is it or not? It is. Okay. It is. Can't I show you? I need to show you. How? Man, we did this. We did this here. Okay? We have already did this. See? So can we see this? Can we see this? How this changes? How we can use this? So A given B. Now we know this that it is something equals to something. See this. See here. See here. Okay. A given by B. A given by B, which is equals to probability of A. Okay, probability of A into the probability of B. So if probability of event A into the probability of event B equals to the probability of intersection of A and B, then then we call this independent. Got it? Okay. Now we are moving with an example. We are moving with the example in which we are rolling two dice. Rolling two die. Okay. And what is the outcome of the first dice? 1, 2, 3, 4, 5, 6. D2. The dice 2. 1, 2, 3, 5, 6. Okay. Now, what is the probability of getting 1 from the dice 1? 6. Okay. What is the probability of dice 2 being 1? 1 by 6. Reasonable? Yes. How? Because for the dice 2, okay, see, in the D2 we have already 1, and it is 1 by 6. Okay. From the other dices, okay, 1 by 6, 1 by 6. Okay. Now, what is, okay, if these are independent, okay, first tell me a thing that outcome from the first dice changes the outcome of the second dice. If 1 comes in here, does it affect the of the outcome of the second dice? No. You can do it by your own. That if you draw a dice, okay, if you get a outcome, does it change the outcome of the second dice? No, absolutely no. Then can we call this event independent? Yes, of course. And if this is independent, then it should be equal to the it should be equal to the event A intersection B equal to probability of event A into the probability of event B, which is 1 by 6 into 1 by 6, which is nothing but 1 by 36, which is 1 by 36. Got it? And this is what we wanted, which is what I want to tell you. Now, moving ahead, we have another topic which is mutually exclusive, which is a very important thing. Okay, mutually exclusive. So, what does mutually exclusive means? So, mutually exclusive means events. Okay, events when they cannot occur at the same time. Those events which cannot occur at the same time. Okay. So if those events cannot occur at the same time, there won't be an intersection between them. We have event A, event B. Okay, and if we do the intersection of event A and event B, and if there is not any intersection between them, or they cannot occur at the same time, then their intersection will be zero. Their intersection will be zero. Because how can they come at the same time if they don't have anything same? Okay. Suppose that event A says that the dice of the die will be odd, and this says even. Okay. What is the event A? 1, 3, 5. B, 2, 4, 6. What is the intersection between them? Zero. If the intersection between them is zero, can we say that they both can occur? No, they cannot occur at the same time. They cannot occur at the same time. So they are mutually exclusive. Mutually exclusive. Okay. Mutually exclusive. Okay. Now, let's take an example, a very beautiful example. If I tell you, then you will get it like this. Okay. Like a blink or a snap or a wink. Who knows? Okay. In the traffic light signal, okay, we are taking the example of the traffic light signal. So we have three lights: red, green, and yellow. Suppose this is yellow. I'm just taking this is yellow. Okay. If there is a red light, you cannot have a green light, you cannot have a yellow light. If there is a green light, you cannot have a red light, you cannot have a yellow light. And if there is a yellow light, you cannot have a green light and cannot have a red light. Okay. So we have a sample space of red, green, yellow. And we have an event A which says the light is red. And we have another event which says light is green. Light is green. Both event occur at the same time? No. No. How? Have you ever seen this? The light is being red and the light is traffic light is being yellow? No, absolutely not. Then these both events are mutually exclusive because they cannot happen at the same time. Okay, okay. Now, and if the events are mutually exclusive, okay, then there is another event probability that will be zero. This is conditional probability, because what the conditional probability says, this by this. Okay, so if this is zero, if this whole term is zero, then anything that then zero being divided by anything will be zero. Then if the events are mutually exclusive, then their conditional probability will be zero. Okay, got this? Very good. Now, how do we use actually the mutually exclusive event with the help of addition and multiplication rules? Okay, or basically, where do we use the addition and multiplication rules? Okay, so in the mutually exclusive event, we know that the intersection between event A and B is zero. The intersection between event A and B is zero. So we use addition rule here. Okay, addition rule here. Did I say probability or like I don't know, I forgot. So the probability of A union B will be probability of A plus probability of B minus probability of A intersection B. That we know, but we know that this is zero in the mutually exclusive. In the mutually exclusive, we know that this is zero. So probability of A plus probability of B minus zero will be nothing but the probability of A plus probability of B. Okay. So this is how we use the mutually exclusive event, and how we find the mutually exclusive event. Because if you're finding a mutually exclusive event, then there is anything common. There is anything common. There is nothing any intersection. Then how can you find the intersection of that event or the joint probability? We need to find the union probability for that using the addition rule. And what does addition rule say? The probability of this event plus the probability of this event minus the intersection of both events. And as we know, the intersection of both events is zero. So we need to minus zero. Okay, got this? So let's take an example with it. Okay, let's take an example. Okay, in the 52 cards. Okay, the example is that we have two events. The event A says that the card will be 2, and we have another event which says that the card will be 3. Now, can we say, is there anything common between them, between 2 and 3? No, nothing. Then what will the intersection of event A and B? Zero. Simply zero. So probability of A. What is the probability of A being 2, getting 2? How many 2 in the card do we have? 4. 4, yeah, in the heart, diamond, okay, spade, club, we have 1, 2, we have 1, 2, we have 1, 2, we have 1, 2, total we have 4. So we have 4 2s in the whole card. And what it will be? It will be nothing but 1 by 13. Okay, and similarly for the B, we have 4 3 cards. Okay, there are 4 3 cards. It will be 1 by 30. Okay, now we need to find the. So can we say these are mutually exclusive? Yes, these are mutually exclusive. If we want to find we need to find the probability of these two events happening of these two events, then we need to find the union probability of A union B. And what is the probability of, and if we know that this is the mutually exclusive, okay, then we know what it is. It is nothing but A plus the probability of A plus probability of B, which is nothing but 1 by 13 plus 1 by 13 equal to 13 plus 2, which will be 0.1. Okay, 0.1 in your hand. Okay, so 1 by 154. Got it? Now, there's a big question which arises in everyone's mind, that what are the difference between the independence and mutually exclusive events? Okay, independence of the event and the mutually exclusive event. Okay, see, if two events are independent, let's say A and B are independent, then they can occur at the same time. They can occur at the same time, or they can intersect. Okay, now we suppose that we have two events which in which we have an event A which says that it is even. Okay, so it will be 2 4 6 and we have a event B. Okay, less than 5. We have another event which says that it is less than 5. So what will be less than 5? 1 2 3 4. Okay, we have this. Now what is the intersection of A and B? What is the if both are independent, then what is the A? What is the probability of A intersection B? Okay, probability of A and to probability of B. What is the probability of A getting it? 3 by 6 into the probability of B, 4 by 6. Okay, and if these events are mutually exclusive, then they cannot occur at the same time. Did you get this? If the event are independent, they can occur at the same time, or they can even intersect. But if 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 the events are mutually exclusive, then there is anything to intersect. There is anything called intersection. Cause there is anything common between them. How can we get the intersection of that? Okay, got this? If the intersection of A event B is 0, okay, there is anything common between them, then they cannot occur at the same time. If they cannot occur at the same time, those events are mutually exclusive. Mutually exclusive, my friend, mutually exclusive. And if the event is independent, okay, they can occur at the same time, even they can intersect, okay, intersect, but they cannot actually affect the probability of another event, given that the first event has already occurred. Okay, if the first event A occurs, okay, if A occurs, it doesn't change the probability of B. Okay, the probability of A doesn't change the probability of B. Got this? So at last, mutually exclusive cannot be independent. Ignore my writing, but let me write it with the beautiful writing. And independent independent events cannot be mutually exclusive. Okay, I hope that you won't have any doubt, and if you have any doubt, you can ask me in the comments, or you can join our Discord. You will have more enthusiasm of AI there. So it's time to wrap this lecture. So thank you for watching till right now. Bye bye, guys, and take care.